Hello guys, welcome back to CFD College. I'm Ashkan and this is another tutorial on Fluid Mechanics 1. In this video I'm going to solve some problems regarding acceleration and velocity in fluid mechanics. I hope you enjoyed my previous tutorials on this course or other software tutorials that I have in my channel. So please subscribe to the channel, share these videos with your friends if you like them, and let them take the advantage of these videos and learn Fluid Mechanics 1. So let's jump to tutorial 4 of Fluid Mechanics 1 at Concordia University. As I mentioned, we have 3 problems regarding acceleration and velocity in fluid flows. Okay, let's start with the first one. Oops, sorry. Problem number 34 of chapter 4. The fluid velocity along the x-axis, here shown in the figure below, changes from 6 meters per second at point A here to 18 meters per second at point B. We know the distance between these points. It is also known that the velocity is a linear function of distance. So it's a linear function of distance along the streamline. So this is our streamline. And we should determine the acceleration at points A, B, and C. Assume steady flow. So the flow is steady. It's important. And we know that velocity is a linear function of distance. So, for example, if this is x-axis, as you can see here, velocity is, for example, u, because it's the velocity in x direction. U is a linear function, so it equals c1 times x plus c2. It's a linear profile for velocity, and it's a function of distance, which is x. c1 and c2 are constants, and we have to find them. So as you know, we need to know the velocity profile in order to find acceleration. So first we need to solve this equation. I mean, we should find c1 and c2. We have velocity at point 1 and point 2. So at point A, we know that velocity u equals v equals 6 meters per second and x is 0. So if you put these values into this equation, u, which is 6, equals c1 times 0 plus c2 equals c2. So c2 equals 6 meters per second. At point B, we know that u equals 18 meters per second, x equals 0.1 meters. So 18 equals 18 meters per second equals c1 times 0.1 meters plus c2, which is 6 meters per second. So from this equation you can find c1 equals 120 meters per meter second. So now we have C1 and C2, so we know that velocity u equals 120 C1, 120x plus 6. This is velocity profile. Now we can find acceleration. As you know, in Cartesian coordinates, acceleration equals delta v over delta t plus v dot gradient of v. As you know, here a and v are vectors, not a scalar. So it means that, for example, ax equals delta u over delta t plus u delta u over delta x plus v delta u over delta y plus w delta u over delta z. And we have the same for a y and a z. You just need to replace these u, this one, and this one, to replace it by v and w. So this is ax, and in this example, in this problem, we only have ax. Why? Because we are at the center line of this nozzle. As you know, as you can see, the streamline is straight from left to the right, so there is no v and w. So from the figure we can understand that, and we can understand that v equals w equals 0. So this term is 0 and this term is 0, and we have steady flow, so this term is also 0. Actually, in fluid mechanics 1, most of the time we work in steady state flow. So knowing this, we can conclude that ax equals u delta u over delta x. And since we don't have any velocity, we don't have the velocity in y and z direction is 0 on this center line, which is a streamline. We don't have any acceleration in those directions. And if you wanna write the equation, see here, for example, ay equals delta v over delta t. This v is not this one, it is velocity, but this is velocity in y direction. So capital V equals u, v, and w, for example. It has 3 components. This v is this one, plus u delta v over delta x plus v delta v over delta y plus w delta v over delta z. And since we don't have v and w on this streamline, this one is 0, delta v over delta x, and v and w are zeros, and this one is 0 because we are in steady state mode. So as you can see, we only have ax in this problem, which is this equation. Now we can find it because we know the velocity profile u. So ax equals u 120x plus 6 times the derivation of u with respect to x, which is 120. So ax equals This one, it's simple. 120 times 120 x plus 6, and the unit is meters per square per second square. Okay, now we can solve it at point A. We know x is 0, so ax equals 120. 120 times 120 times 0 plus 6. So at point A, the acceleration in x direction is equal to 720 meters per second square. So A acceleration at point A equals 720 in x direction, I, meters per second square. At point B, we know x equals 0.05 meters, so ax equals 120 times 120 times 0.05 plus 6. So ax at point B equals 1440 meters per second square. So A at point B, acceleration at point B equals 1440 in x direction, meters per second square. And at point C, it's easy. X equals 0.1 meters, so ax equals, you can do the math, it equals 2160 meters per second square. So A acceleration at point C equals 2160 I meters per second square. This problem was easy. Actually, this part of the course is not too difficult, and you can solve the problems. The second problem number 51. Air flows from a pipe, here we can see, into the region between two parallel circular disks. So here is the radius, outer radius of the disk. This is our coordinate. Here is the pipe and inflow, and these are the disks. As shown in the figure below, the fluid velocity in the gap between the disk is closely approximated by this equation. So although we have a gap, we know the velocity profile along the radius. See this, we know the velocity profile at each section, at each radius. It's uniform. Where r is the radius of the disk, r is the radial coordinate, and v0 is the velocity, fluid velocity at the edge of the disk. So v0 is here. Determine the acceleration for r1, 2, and 3 feet if v0 is 5 feet per second and the outer radius is 3 feet. Okay, so we should find velocity and the acceleration. In this problem, we should work in cylindrical coordinates. In the previous one, we worked in Cartesian. In cylindrical coordinates, acceleration equals as in s direction. S means streamline, or streamwise plus an in normal direction. So we have a streamline or a streamwise acceleration. I called it a streamline, and normal acceleration. As you know, as equals v delta v over delta s. S is streamline direction, while an normal acceleration equals v square divided by r, or let's say the local radius. The radius of the this is not this local r coordinate, it's the radius. Let me show it by for example r prime. It's the radius of the curvature. For example, if this is a streamline, it's a curvature. Here is, for example, the center of this arc, of this curvature. This point, this is r prime. As you can see, here is, for example, this is the flow, this is flow direction. So this is a s, or let's say this is streamline direction, and this is normal direction. So we have r prime, and these are normal and streamwise streamline directions. This r prime is the radius of this curvature. So if you had straight, imagine this is straight. Okay, if you had a straight streamline, for this streamline, this r prime is infinite. So an for straight streamline equals 0, because an equals v square over r prime, which is the radius of the curvature, and for a straight line r prime is infinite. So an is 0. Let's get back to this problem. Okay, so as I mentioned, acceleration equals as in s plus an in normal direction. As you know, an equals 0 in this problem, because the streamline is horizontal. As you can see, this is the r and this is the streamline. You can understand that by this velocity profile. This profile is perpendicular to r, and it's uniform, so it so it shows us that a streamline is straight towards the outlet. So since the streamlines are straight, an equals 0, so we only have as. Acceleration is in a streamline direction. As equals v delta v over delta s. What is velocity? Velocity equals v naught r over r. V naught and r are constants, but this is the coordinate, and we have to relate r to s. Why? Because we need the derivative of velocity with respect to s. in order to find AS. So look at here, this is the streamline and this is R coordinate. Since S and R are in parallel, you know, the delta R equals delta S. It means that if I move from here to here, which is delta S, it means that it's equal to this distance. It means that it doesn't, how can I say? Let's say it's equal to this distance where, I move from this point to this point in radial coordinate, in R coordinate. So it's delta R. You will see in the next example, the next problem, where we have this streamline, the flow moves from right to left, while the R coordinate is in this direction, from left to right. In that problem, as you can see, if I move along the streamline coordinate from this point to this point, which is delta S, it's in the opposite direction, where on R coordinate. So this is minus delta R, because I'm moving in the opposite direction with respect to R. So in this problem that we are solving now, delta S equals delta R, while in this problem, the next problem, delta S equals minus delta R. So you need to think about it, whether streamline and R coordinates are in the same direction or in opposite direction. So here in this problem, delta V AS equals V times delta V over delta S. This is equal to V over delta V times delta V over delta R. As I mentioned, delta S equals delta R in this problem. Now we can find the acceleration. V is V naught R divided by R, and the derivative of velocity with respect to R is minus V naught R over R square. So the acceleration in streamline direction equals minus V naught square R to R square divided by coordinate, the lowercase r to the power 3. Acceleration is and has this negative sign. Actually, it's negative, meaning that the acceleration, the velocity is decreasing. Why? Because if we look at this system from the top view, this is the pipe and the flow comes from the pipe, and this is the direction of the airflow. As you can see here, this is, for example, A1, and at this section we have A2. As you know, Q equals V1 A1 equals V2 A2. Since A2 is greater than A1, and we know we have continuity, we have mass conservation, so the flow rate should be constant. This means that V1 is greater than v2, it means that the acceleration should be negative. Okay, now let's get back to the problem. We have to find the acceleration at 3 different radius. At r equals 1 feet, a, which is equal to as, in a streamline direction, equals minus, let me make it more simpler, minus, we know v naught, which is 5 feet per second, minus 5 feet per second square, times the radius, which is 3 feet to the power 2, divided by r to the power 3. This r has the unit of feet, so we have minus 225 divided by r to the power 3 feet per second square. So at point A, at a radius equals 1 feet, the acceleration equals minus 225 feet per second square. At r equals 2 feet, the acceleration equals as in s direction equals minus 28.1. So you need to replace r with 1, 2, and 3 feet. It's easy. Feet per second square, and at r equals 3 feet, a equals as in a streamline direction equals minus 8.33 feet per second square. Let's jump to the last problem in this tutorial, problem number 52. Here, as you can see, we have an opposite situation. Here the velocity, the flow comes from the outer edge and moves toward this pipe. So it's in the opposite direction, as you can see. We have airflow into a pipe from a region between a circular disc and a cone. As shown in the figure below, the fluid velocity in the gap between the disc and the cone is closely approximated by this one. So we know the velocity along the radial coordinate, at different sections. We can find velocity because we know this velocity distribution. R is the radius of the disc. Lowercase r is radial coordinate. V naught is fluid velocity at the edge of the disc. We know them. R equals 0.5. Oh no, sorry. R is 2 feet, the capital R, and V naught is 5 feet per second. We should determine the acceleration at r equals 0.5 and 2 feet. So everything is just the same as what we did in previous problem. As you know, the acceleration equals as plus an in normal direction. As I mentioned before, here, as you can see, this is the streamline. The streamline is straight. You can understand it by this velocity distribution, which is uniform. It means that we don't have any velocity gradient in theta direction. So this is the streamline, which is straight. Actually, it's for simplicity, and in reality it's just the same if the gap is small enough. So this assumption is not bad. As you can see, this is so that this is the streamline, and here you can see this is our coordinate, and as I mentioned here, R and S are in opposite direction. So in this case, delta S equals minus delta R. Since streamline is straight, R prime equals infinity, so an, which is equal to v square over R prime, equals 0, and we only have as, and as you know, as equals v delta v over delta s, and in this problem equals minus v delta v over delta r, because r and s are in the opposite direction. Okay, we know velocity equals v naught r square over r square, and from these we can find as equals minus v naught r square over r square times the derivative of velocity with respect to r, which is minus 2 v naught r square divided by r to the power 3. So as equals, we have two negative signs, they cancel each other, so r equals 2 v naught square capital R to the power 4 divided by r coordinate to the power 5. And as you can see here, acceleration is a positive value, because as we move towards the pipe, as you can see, the area decreases, and since we have continuity in mass, the velocity should increase. Okay, now we can find at r equals 0.5. Let's determine this first. As equals 2 times v naught, which is 5 feet per second square, times r, which is 2 feet to the power 4 divided by r to the power 5, equals 800 over r to the power 5 feet per second square. So if r equals 0.5 feet, as equals 800 divided by 0.5 to the power 5 feet per second square. So a equals as in s direction equals 600 feet per second square, and at r equals 2 feet, as equals 800 divided by 2 to the power 5 feet per second square. So a equals as in s direction equals 25 feet per second square. And this is the end of this tutorial. We solved 3 problems regarding acceleration and velocity. I hope you enjoyed it and learned Fluid Mechanics 1. Thank you for watching this video. Please share these videos with your friends, and I have lots of videos on numerical simulations and post-processing in this channel. You can enjoy them too. So please subscribe and give us a thumbs up. Thanks for watching this video. Until the next video, take care of yourselves and bye bye.